All right, give yourselves a big hand. We've done 5 quizzes in the class. We've got one last one to go, which is sort of a bonus in the sense that I dropped the lowest quiz. We've also gone through what I consider to be some of the most intellectually challenging material of the course. We brought in ideas of mechanism. We brought in ideas of synthesis. And now we're kind of winding up the course, and I want to cover some topics that are, I think, more interesting, and in some ways bring back some old themes and bring in some new themes as well. So we're going to spend today, and we're going to spend Thursday talking about carbohydrates. And carbohydrates, in one way, is a very old topic in organic chemistry. Carbohydrates, sugars, are central to so much of life. They are, of course, the sugar that you put in your coffee. They are the glucose and fructose that make up that sugar. They are the components of starch and cellulose. In other words, paper on your desk and the cornstarch and so forth, and potato starch in the vegetables that you eat. They're the backbone along with phosphates. Sugars, ribose, are the backbone of DNA. They're attached to many biologically active natural products. Sugars coat the surfaces of your cells. Your blood types are determined by which types of sugars you have on the surface of your blood cells, and in turn give you antigenicity, give you an antibody response to getting the wrong sort of blood type if you get an infusion. So sugars are fantastically important. We are coming back to an old theme that you learned in 51A, and that's stereochemistry. And I think the toughest thing about learning sugars isn't the stereochemistry, it's the different representations and interrelationships. And we're going to spend some time today talking about structure and stereochemistry of sugars. I spent last night and this morning making some special tools for you to help understand some of the representations that are often used. Personally, I'm a big fan of plastic models. Remember the Darling models you used in 51A and maybe in some of the so-called dry labs associated with your course. And I recommend you bring them back to learning this chapter. Oh no, I see tears here from the models. You can also use your computer. I will let you use models on the final exam, so it's useful to have them, plastic models, so it's useful to have them complement things. All right, I want to start with literally a simple sugar with sort of the most fundamental, or maybe the most common sugar, and we're going to draw it in a chair conformation. And the sugar that I'm drawing here is glucose. And it's kind of easy. I like it because when I draw my chair like so, all of the substituents are in the equatorial position, so it's very easy to remember the structure of glucose. Now, sugars have an aldehyde group, and we're going to talk more in a second, but for the most part they exist as cyclic hemiacetals. And I'm going to draw, we have another stereocenter for a cyclic hemiacetal, and I'm going to draw that hydroxy group at this position, at the 1 position that we'll learn is called the anomeric position. I'll draw it equatorial. This molecule is called beta-D-glucose. And so it's a member of the class of carbohydrates. I guess if you go to the gym, you might call them carbs, of course. It's a nickname. Its molecular formula is C6H12O6. And if you think about it, then the reason it gets its name as a carbohydrate is that the formula is carbon plus H2O. And literally, if I take some sugar, if I take some table sugar, and I take sulfuric acid, which is very dehydrating and can yank all the water out and carry out a whole bunch of reactions. If you've ever seen this done, you just put it in a beaker, put some sugar in a beaker, pour on some consulfuric acid, and this big snake of carbon comes out of the beaker, this big rod of frothy carbon and sulfuric acid, along with a little bit of smoke and so forth. Anyway, I'm not going to do that demonstration here, in part because it's kind of hazardous, but it's a lot of fun. So glucose is a member of a class of carbohydrates, a broad class of carbohydrates that we call aldoses. And the reason we call it an aldose is that when we go ahead and unwrap the structure, when we break up the hemiacetal at the 1 carbon, you get an aldehyde. There are also sugars where if you break up the hemiacetal, you get a ketone, and those are called ketoses. We'll talk about those later. Glucose is a 6-carbon sugar. We number it from this position 1, 2, 3, 4, 5, 6. And so glucose is called an aldohexose. Hex is 6. And I guess to be consistent, I will write an aldose to indicate it's one of many, many. There are a bunch of other things get called. Because glucose has a 6-membered ring containing an oxygen in the closed form, in the hemiacetal form, we call it a pyranose sugar. Pyran is a 6-membered ring containing an oxygen atom. Tetrahydropyran is a saturated 6-membered ring containing an oxygen atom. So glucose is a derivative of tetrahydropyran, so we call it a pyranose. The other important ring containing oxygen is a 5-membered ring containing an oxygen. The aromatic compound with double bonds in it is called furan, and if you have all hydrogens on the ring, if the ring is fully saturated, you call it tetrahydrofuran. Tetrahydrofuran, we've seen that THF is the solvent, and so there are other sugars that have 5-membered rings in them that you would call a furanose or a furanose form of the sugar. And I guess as long as we're talking about names here, we would also refer to glucose as a monosaccharide. Mono, of course, means 1, saccharide, well, sugar. I want to give us some contrasts in structure and in stereochemistry by drawing a disaccharide at this point. And it's going to introduce some basic concepts here. So we're going to start with drawing another pyranose form of a ring. We're going to have 2 of these linked together, so 2 chair cyclohexanes. And I'm going to go ahead and draw everything the same on this ring as I did for glucose, except at the 4 position, I'm going to, instead of having the hydroxy group in the equatorial position, I'll put the hydroxy group in the axial position. And we're going to make a molecule with 2 sugars in it. It's one that you might have consumed this morning, one that actually is good for you. Well, maybe, I guess all sugars are okay in moderation. Okay, so we're going to link to another ring here. And this ring will have, as a glucose type ring, like so. So here's our disaccharide. Disaccharide is lactose. guess my drawing isn't the prettiest in the world. I'm always delighted when I look at people's notebooks and see their drawings so much prettier than mine. So lactose is a disaccharide. And I think there are a couple of interesting take-home messages that we get from this. First of all, sugars can be linked together one to the next to the next. Starch, for example, is a long, long chain of sugars, as is cellulose, basically a polymer of almost infinite length. Now, you might look and say, well, it's a little different looking than glucose. I mean, we've basically formally removed one water molecule. So if you write out the molecular formula of lactose, it's C12H22O11. And so you'd say, well, we don't have the same ratio of carbon to hydrogen as we had because we've connected in glucose. But if you notice, it's still a carbohydrate. It's still effectively carbon plus H2O. In this case, 12 carbons plus 11 H2Os. In the case of glucose, 6 carbons plus 6 H2Os. So if you look at our lactose, as I said, we have 2 units in it. We have our glucose unit. And now we have another sugar unit in it, and this is a galactose unit. So galactose, let me draw out galactose and glucose in just a second, but I just want to make one last point. We have a linkage from the 1 position of glucose, right? So this is the 1 position, and then to the 1 position, I'm sorry, of galactose. And that's the 4 position of glucose, right? We number our way around the ring 1, 2, 3, 4, 5, 6. And so we call this a 1 to 4 glycosidic bond, glycosidic linkage, or glycoside bond. I want to draw out the units, the subunits here in galactose. So I'll draw out the 2 sugar units. I'll redraw glucose again. It pays to practice a little bit in your drawings, and I've got to say I'm no artist as far as cyclohexane rings go. Basically, the theory is you're going to be making parallel lines. So the equatorial bond for this OH group is parallel to the CO bond for this one. The equatorial bond to this OH group is parallel to this one. As I said, I'm not much of an artist, but I can get my ideas across competently. All right, so galactose, so this is glucose, or more specifically beta-D-glucose. We'll talk about what that D means in a second. And now we'll draw galactose, more specifically beta-D-galactose. I'll talk more about that beta in a second. All right, so everything is the same over here, except as I was indicating when I drew our molecules, now we have a different stereochemistry at the 4 position. So 2 isomers that have the same connectivity, all of the same atoms connected together in the same way, but just differ in the stereochemistry of 1 position, are diastereomers. They're stereoisomers that are not enantiomers. Remember, when you learned about stereochemistry, you learned about enantiomers, compounds that are non-superimposable mirror images. You learned about diastereoisomers, stereoisomers that are not enantiomers, and then you learned about constitutional isomers, molecules that have different connectivity, different arrangements of atoms. All right, at this point, I want to draw another structure, and I'm deliberately proceeding reasonably slowly and methodically here because I think it really takes some time to bring all these ideas into your head and to dust off the cobwebs on some of the stereochemistry and structure that you learned back in 51A. So I'm going to draw a different structure here. We're going to do everything the same as glucose, with one exception. I'm going to now, instead of having our stereochemistry at the 1 position be equatorial, instead of having the hydroxy group at the 1 position be equatorial, I'm going to have our hydroxy group at the 1 position be axial. Now this is alpha D-glucose. And in the convention of organic chemistry, you have beta as the up position, the top face of the ring. Alpha is the bottom face of the ring. So the OH is pointing down to the bottom face as we've drawn it at what we call the anomeric carbon. So the carbon that makes up the hemiacetal occupies sort of a privileged position if you think about it, because unlike all the other positions, your stereochemistry there depends just on how you've closed the hemiacetal, whether you've closed it so that the OH group is equatorial or axial. And so because of this very special diastereomeric relationship, in sugar chemistry, we often have yet another word for diastereomer involving the hemiacetal. It's a labile position. So we give it a special name. As I said, this is the hemiacetal position. And so we call this an anomer. So just as we would say that beta D-glucose and beta D-galactose are diastereomers, we would say that alpha D-glucose and beta D-glucose are anomers. They have a special diastereomeric relationship to each other. They're still diastereomers, but they're a special type of diastereomer that often gets called an anomer. So I'll write that down. So most diastereomers are stereochemically stable. In other words, if I have a bottle of lactose and I go away for a long time, and travel around the world and come back, I still have a bottle of lactose. It would never become a bottle of, I'm sorry, if I have a bottle of galactose, it would never become a bottle of glucose. If I have an aqueous solution of galactose, it is stable as galactose. But this is not the case for anomers in which you have a hemiacetal. We've already learned that hemiacetals are not stable compounds. They are in equilibrium with aldehydes. Now, in the case of cyclic hemiacetals, we learned that they tend to favor the closed conformation. In the case of glucose, that's really, really, really strongly a preference. And nevertheless, at equilibrium, you have a teeny tiny bit of the aldehyde form, of the open form. In other words, alpha and beta D-glucose can interconvert in water and exist in equilibrium and so I'll write this as an equilibrium. I'll say in water because in the solid state the crystal lattice keeps them stable, but in water you have all sorts of chemistry occurring involving carbonyl groups. And so the alpha and beta forms of D-glucose can interconvert. At equilibrium, you have a 36 to 40 to 64 ratio. And I want us to think ourselves through this interconversion process, and I'm going to sketch it out here in our mind's eye. So I'll start with alpha D-glucose. We're not going to write a detailed mechanism. I think by this point, I'm hoping that you are on top of carbonyl chemistry enough to be able to work through the mechanism. Remember, in the case of a cyclic hemiacetal, catalyzed by acid or by base, but we'll think acid. And even in water, you have a little bit of acid. You have 10 to the negative 7th molar H3O plus in neutral water. You can protonate all your oxygen atoms. If you protonate this oxygen atom, you can open the cyclic hemiacetal. And so I'll write a tautomer here. I will write the isomer in which we've opened this linkage. And so now we have our aldehyde. Everything else is the same. So we've just opened our linkage here to form the aldehyde. Remember, mechanistically, you can think of protonate on this oxygen, push electrons down, kick out that oxygen. Now you have an oxocarbenium ion, take off the proton. All right, now if we imagine rotating about this bond here, like so, and I'm just going to say we're talking equivalent structures here. Generally, when you rotate about a bond, you don't think about a structure as being different. You think about it as being as just being a rotamer. So I will rewrite rotating about the bond here, like so. So all I've done differently now, oops. Is rotate about the bond to the aldehyde. And now, if you imagine closing up the structure here, so we've started with alpha D-glucose. We've envisioned opening it to form the aldehyde. At equilibrium here, you have about 0.003% of the open form at equilibrium. And now, if you imagine just reclosing this, we've gone to the beta form. We've gone from the alpha anomer to the beta anomer. Question. Can you do that for lactose? Great question. Yes and no. In the linkage. So the question is very, very good. And I'm glad you asked it. Okay. Oh, lactose, not, yeah, lactose, right. Absolutely, very good question, and I am delighted that you asked it. So let's go back to our lactose structure. All right, in our lactose structure, there are two types of anomeric carbons, two types of carbons at the one position. There's this carbon, which has a hemiacetal, and then there's this carbon here, which has an acetal. Remember, a hemiacetal has a hydroxy group on it. An acetal doesn't have a hydroxy group on it. And so the hemiacetal form absolutely can equilibrate. And so the structure that I drew for lactose that's in your milk and whatever you drink in the morning on your cereal, cream in your coffee, the lactose that's there, the lactose that's in your ice cream, has an equilibrating mixture of the beta and alpha anomers in the glucose unit. However, unless you have strong acid, and by strong acid now I don't mean neutral water or a little bit of dilute HCl, but unless you have a very strong acid that can break apart an acetal, boiling HCl solution or boiling acid, the linkage, the beta linkage off the galactose unit is stable and doesn't undergo interconversion. So I will write stable over here, and when something interconverts, we say it's labile for this position. Good question, good thought. Other good questions?
Can a galactose have a carbon 1 steric shift? And if so, what will that molecule be called?
Can galactose, so the galactose unit, this subunit here, at carbon 1, free galactose? Absolutely. Okay, great. Another great question. So, and I want somebody to answer for me here. So we saw that I drew the beta compound. What do we call this form of galactose? Alpha. So this is alpha D galactose. And I'm going to tell you something else right now. So it's really good to have a few pieces of core knowledge that you keep in your head because you use those. We've done this when we talked about pKa's. I talked about, know the pK of a ketone, call it 20, whether it's a ketone or an aldehyde. Know the pK of an ester. Know the pK of LDA. That core knowledge is very useful because you can build on it. There are lots and lots of different monosaccharides. I do not, in my own head, I'm not a practicing sugar chemist, keep all of the structures of all the different monosaccharides. I could if I wanted to, but it's just not useful for me. But glucose and, say, the 1-diastereomer galactose are useful things to know because it's something that you can hold on to, and then you can build on it. So when you see various other sugars, you see talose or something, you can understand relationships to them. Other questions at this point? Yeah. Why is it that if you change the position at the one group, if you change the stereochemistry at the one position, it's not a different sugar, and if you change it at the 4, it is? Same basic idea. Because alpha and beta D-glucose are labile, because they interconvert, we'd say they're rapidly interconverting, they're the same basic molecule. But for ones where you have stable diastereomers, then you'd say they're different. They're very, well, I mean, they're both different, but there's this question of time scale. If I put beta D-glucose into a bottle and come back, I have a mixture in water of alpha and beta D-glucose. So they're different, but they're not that different. They interconvert. So that's why we categorize them. And actually, let me build on that a little bit. So beta D-glucose has an optical rotation . Optical rotation means the amount that you rotate plane polarized light. If you've ever taken a pair of polarized sunglasses and crossed the lenses, you know that when you get to a 90-degree angle, light doesn't come through. Or if you ever have a pair of polarized sunglasses and you put them over, if you have an LCD watch or an LCD, maybe even the LCD screen on your phone or computer, and you rotate it, you will black out because you have polarized light in many of these sorts of devices. It will go black at one angle, and at a right angle it will be completely transmitting of, or fully transmitting of light. And it's the same type of thing with sugars. They rotate that polarized light, and this is one of the characteristics of optically active molecules, of molecules where you have a single enantiomer and they're stereochemically active. And the degree to which glucose rotates plane polarized light is called the specific rotation. And if it's used traditionally, the sodium D line, that bright yellow line, if you've ever been to the East Coast, you've seen lamps on the, you've seen lights on the highways there. Those bright yellow lights are called sodium lights. That's a 522, I believe, nanometer light. Anyway, that one is often used, and you rotate it by 19 degrees. Now, alpha D-glucose is a different stereoisomer, and so it rotates plane polarized light to a different extent. The optical rotation of alpha glucose is 112 degrees. They call it specific rotation if you want to be exact in what you're calling this rather than optical rotation, but optical rotation I think is a little easier to understand. Now, what's cool about glucose, and this comes back to your question there about why we don't consider them different molecules, or we consider them different but not that different, is if I go ahead and take my solution of beta D-glucose with a 12-degree optical rotation, a 12-degree specific rotation, and I let that solution sit, you can see the glucose interconverting from the beta isomer to the 36 to 64 mixture of beta and alpha, because the rotation changes with time. It goes, so upon standing, we'll say, both of these end up going to 53 degrees rotation, 53 degrees specific rotation, because the two anomers are interconverting. We call this process mutorotation. Muto is change, so basically that's a fancy way of saying changing rotation. And it's going to be catalyzed by a little bit of acid or base, but as I said, even neutral water has acid and base in it. 10 to the negative 7th molar hydroxide, 10 to the negative 7th molar hydronium ion. So in other words, the catalyst would just speed up the process. Thoughts or questions at this point? All right, I want to talk about how we represent sugar structures. And there are sort of 4 different notations for drawing. I mean, the big problem we have is the fact that we're dealing with a flat blackboard, and yet you're talking about molecules that are rich in stereochemistry. And so thinking about understanding, communicating, and interrelating stereochemistry is really critical when we think about sugars and their structures. So we've been drawing the chair form of beta-D-glucose, and so I'll draw that again because we're going to start to compare. And so here we go. Here's our beta-D-glucose. And at this point, I want to remind us of something. I want to remind us of where our hydrogens are. Not the hydrogens of the OH groups, but the hydrogens that have been implicit in the molecule. So of course, even though all of our groups on the cyclohexane ring are equatorial, except if you have alpha glucose, in which the alpha D-glucose OH is axial, we have hydrogens. So in beta-D-glucose, we have an axial hydrogen. And at the 2 position, we have another axial hydrogen, and ditto at the 3 position. And the 4 position, the position that galactose had an axial hydroxy group, we have an axial hydrogen. And finally, at the 5 position as well. So in a way, we have 5 stereogenic centers in the molecule. The stereogenic centers at positions 2, 3, 4, and 5 that are fixed. The one at position 1 that's labile. And of course, position 6, being a CH2OH group, you have 2 hydrogens on the carbon. It's not a chiral carbon. So there are other ways that we can represent the structure here. So again, I'll just write beta-D-glucose to remind us of the structures I'm going to be writing for all of these. So there's another way of representing the structure that doesn't try to represent the conformation of the ring. Remember, writing a cyclohexane ring, writing a 6-membered ring in the conformation that I've written there is a projection. If you physically take a plastic model of cyclohexane in a chair conformation and hold it in front of a light source like an LCD projector and let the physical model project on the screen and tilt it into just the correct angle, you will see all of the bonds project on the screen like this. It's still a 6-membered ring, but that's the projection. That's why we write it that way, to think about and to communicate stereochemistry. If we choose not to try to represent the shape of the molecule, you can still communicate the stereochemistry. So one of the ways that people do it is just to do a flat ring, and again it's sort of tilted. We're going to go ahead and use wedges to represent what's coming out of the board at us. So we sort of have our ring tilted like this, but we're just representing a planar structure. And now you can think about it. We can simplify things. We can write our anomeric OH up and the hydrogen down. So obviously this is a more stylized representation. It's not trying to capture the physical structure of the molecule. We can take our next position. Remember, we have our hydrogen down, our OH up. We can take our next position. We have our hydrogen up and our OH down. So we can represent that like this. We come to our next position. Now the hydrogen's down, the OH is up. So we can represent that like this. Position 4, hydrogen up, OH down. And finally, position 5, and we have hydrogen down, CH2OH up. We call this representation a Haworth projection, and you'll see it used liberally in your textbook. So those two projections kind of represent the cyclic structure of the molecule. And they catch all the key stereochemistry, but they also require a little bit of artistry to represent. And there are ways of representing the structure that maybe involve less artistry. If we imagine opening the structure, to an aldehyde at this position, and now we want to get all of our stereochemistry just in a zigzag structure of the molecule. So I can imagine going from one end to the other. We have 6 carbons and an oxygen on the end. So one carbon, 2, 3, 4, 5, 6. And let's make let's start with the aldehyde carbon here. Remember, I'm just opening the hemiacetal structure, so that's going to be the aldehyde. And now our chain zigs up. So in looking at the chain at this point, the OH is going to be coming out at us. The hydrogen is going back. So in our zigzag structure, we're going to represent this as our OH coming out, our hydrogen coming back. It's important to be able to visualize these relationships. And it can also be very hard to do this the first time around because you're having to train your head to really recognize three-dimensionality embodied in a two-dimensional drawing. Okay, our next position on the chain, we've zigged down. The OH is again coming out at us, and the hydrogen's coming back. So we're going to represent that over here, OH, hydrogen going back. Now you almost want to continue to walk around and look at this molecule from over here, like I'm doing. Oh, that OH is coming out, and the hydrogen is going back as we come around the chain. Now we continue along here. You have to sort of position your eye from back here and say, okay, now that OH is going back. So we sort of followed our way. You've unwrapped the chain. You're visualizing from here. That OH is going back. That hydrogen is coming out. And this is just our CH2OH group. And so what I've done here, in part because I'm used to seeing molecules like this, is I've unwrapped the structure, drawn it in a linear fashion as the aldehyde. And honestly, when I think about lots and lots of stereochemistry in organic molecules, the structures that I think about are linear zigzag structures like this and cyclic structures like that. What's that? The hemiacetal. Yes, so can I point to the hemiacetal? Is that position 1? And so we just imagine this interconversion of the hemiacetal and the aldehyde. Remember, this open form is present 0.003% amidst the closed form of the molecule. And the closed form is a 64 to 36 ratio of the beta and the alpha anomers. Other thoughts and questions? All right. Now, the one that I am not in love with for a representation of molecules of sugars, but that has been used traditionally to such an extent that it is absolutely integrated into almost all textbooks who discuss sugars, is what's called the Fischer projection. And in a Fischer projection, what we're going to do is represent the molecule in a straight line. And we're going to represent it so it curves backwards, but we're going to show it as linear. We'll put the aldehyde group on top, traditionally. And now we're going to look down this way so you can sort of see, all right, as we do this, we're going to get CHO here. And then OH and H, we're basically sighting down this position here. I'm going to help you out with this some more in just a moment. So we're sighting down this position here. But the key thing in the Fischer projection is we're basically wrapping the molecule on itself. So you would have to imagine as we continue, we're going to go ahead, rotate about this bond 180 degrees, bringing it down. That's going to throw the OH pointing out, pointing back on the other side. So we're going to rotate 180 degrees, like so. Now that's hard to see. For me, the way I see this is really the relationship. I can easily see the relationship between the cyclic structure and this acyclic structure. I just sort of walk around in my mind looking at it, and it helps to train yourself with models, and we'll come to that in a second. Plastic models are the best, but computer ones work. The Haworth projection is perfect for converting to the Fischer projection. Because the Haworth projection, you say the molecule's already wrapped on itself. Here's the molecule, and remember, that's just an aldehyde, so we're going to ignore stereochemistry there. I'm going to pick that up. This OH, when I pick it up, is going to go off that way. This OH is going to go off that way. I take the structure, I pick it up. Here was the OH, I bring it vertical, that OH is that way. I take the structure, and here is this OH. I bring it this way. That one's pointing to the left. And we can continue around like so. And now the only point that gets confusing is over here. Let me draw how glucose is drawn first, and then I'll show you how we get over there. So the last position doesn't map well. and I'll show you why in a second. So here's our last position. And in fact, for all of the D sugars, they have this stereochemistry at this position, at the position that's next to the terminus of it. So D at this position, they didn't know it when they first started. Fischer started to study the stereochemistry of the sugars, but the D means this stereochemistry, and it means R stereochemistry. Remember R and S at this position. All right. Here's our Haworth projection again. I want to show you what I see when I go ahead and do this. When I go ahead and do this, I'll draw this on this blackboard here. So we look and we say OH, H, OH, H, OH, H. Now we come down to this position. Remember, I've picked up this ring. We're curving back on ourselves. We've picked up this ring. It's like this. I brought it like this. So we have this high OH over here, this second OH, the one at the 3 position here, the one at the 4 position over there. Now we come to the 5 position. If I pick this up and look at it, what I have over here is now I have a carbon, but I have the OH continuing down, and I have a hydrogen, and I have a CH2OH over here. In other words, I pick this up, I look, I say, how does it go? Okay, well, now when I pick this up, that hydrogen's off to the right, the CH2OH is off to the left, the oxygen is down when I've picked this up. But now you say, okay, how do we get from there to there? You can just imagine that you rotate about this bond. So you rotate like so, like so, like so. You move those 3 atoms all in a circle. You're rotating about this bond. Everything's the same until we get to the bottom position and its representation. And now we've rotated, so we've rotated the OH over to here. We've rotated the hydrogen over to here. And we've rotated the CH2OH over there. And that's hard to see. It's easy to see with physical or computer models. It is hard to see in your head for the first time, particularly seeing this representation. Remember, this representation is the molecule, the sugar molecule, wrapped around a cylinder here. It is taking that Haworth projection and wrapping it. And so one of the things that I did in trying to help you get ready to see this is I set up some stuff, and we can pop our computers here at this point, because I'm going to go ahead, and you're welcome to play along. Johnny and Kim and I will be able to help you with this in your discussion section or in our office hours if you like. But I've set up a tool for us here on the website. And I just set it up in PyMOL. So if you remember back to week 3, we had PyMOL and we had some exercises, and you downloaded PyMOL onto your computer, and I said, well, use it later. I want to use it later in the course. So okay, so now is later. So I've made some molecular models for you. And what I've done is I've started with those drawings that I just made on the blackboard. I started with the chair conformation of cyclohexane for glucose. I started with the Haworth projection, the zigzag structure that I just drew, and the Fischer projection. And what I did for you last night was I created molecular models of each of these. So here, for example, is the chair conformation of beta-D-glucose. And remember what I talked about with the idea, whoops, let me kill the, oh, I guess that is as killed as it, okay. That'll go a little better. How's that? Okay, so remember I talked about projections, and this goes right back to Chem, to our very beginnings. So there's the six-membered ring. When you go ahead and rotate it like so, your chair emerges. I've linked, by the way, I've linked Firefox in my computer so that PDBs download and open automatically in PyMOL. So, okay, if you want to go ahead, remember show can show the sticks here. And so that can show your structure in sticks. I just went to show in sticks we can get our structure. Okay, I'm going to bounce back. I want to show you what I laid out for you right now. So, okay, so the Haworth projection should just pop up. If it doesn't, all right, so I've made an unnaturally flat cyclohexane, an unnaturally flat sugar molecule. And so now, when you start to look, so there's our Haworth projection. Pretty much just as I've drawn it. And I'll show you a couple of other things here. I'll show you what I laid out, and then I'll show you how I use these tools to think. Okay, I'm going to show you the open form, the zigzag form. So there's our zigzag form that I just drew out on the blackboard for you. You can get a good look at it. You can see all your stereochemistry on there. And now the last thing I laid out for you was the Fischer projection with unnaturally flat actually, the next to the last thing I laid out was the Fischer projection. So I'm just going to move the aldehyde to the top. And so that's the Fischer projection. All right. So let me see if I can get our Haworth projection next to our Fischer projection. All right. So remember what I said about rotating the structures. So here we go. All right. So that's our anomeric carbon of the Haworth projection. That's our 2-carbon, and you'll notice the hydrogen's off on the left, the OH is off on the right. This is our 3-carbon. You notice the OH is off on the left, the hydrogen is off on the right. We'll continue around. I'm going to rotate my Haworth projection. So now we come to the 4-carbon. And now you notice the OH is off on the right. That's the 4-carbon here. And then I'm going to continue to rotate here. And now this is the conundrum I mentioned. So now we're at the 5-carbon. And so the 5-carbon we have here, the hydrogen off in the cyclic form, the CH2 off on the left, and the oxygen that's off. And you just have to imagine rotating about this bond here, which is going to bring that hydrogen there, this CH2OH down and this OH here. I'll do this in the Haworth projection here like so, as best as I can, because of course the carbon is tetrahedral. And so there we go. Now you can see our 5 position, the hydrogen's off to the left, the OH oxygen, the oxygen that was the anomeric acetal is now off to the right. All right. Last thing I've done for you to give you some tools. See, these structures, and this is what I was saying before, glucose is really an archetype of all the sugars. If you can master glucose, you can master all the other sugars in your thinking, and if you can understand these structures. So you have one sort of tool here, one sort of toy. Okay, the other thing I've done for you is PyMOL's native file format. PDB is sort of an interchange file format. It's also one that I've linked so my computer opens it in PyMOL when I download it in Firefox. PSE files are the native format for PyMOL, so they contain all of them. So I made a composite structure, and I want to show you how to use this on your own. So here's a one I call glucose composite. It's just going to go to my downloads window. All right, so there's my glucose composite, and I want to show you what's in here. So there's glucose in the chair form. If I click on the right here and I close the chair form, there's my Haworth projection. If I click again on the open form, there's the open form. If I click on the Fischer projection, there's the Fischer projection. I can just rotate it up. And so these tools or plastic models should help you visualize this stereochemistry and really, really internalize it. Now, the last thing I want to do is just come back to our drawings, and I just want to play off of these drawings that we had here. Okay, so let's come back. This is our Fischer projection of glucose. All right, what I want to do now is to come back and show how handy these structures, these Fischer projections are for visualizing other stereochemistry. So remember, we said galactose was identical to glucose except in the 4 position. So now I look at galactose and I say, all right, I know how. If I know the glucose structure, all I need to do to make galactose from the Fischer projection of glucose is to change the stereochemistry at the 4 position. 1, 2, 3, 4. All I do now is swap those 2 substituents. And this structure is beta D. Well, I'm sorry, actually, technically, because we're not showing the cyclic structure, I should say this is D-glucose. And so technically, this is not beta or alpha, but it is regardless D-galactose. All right, so the main point is we go through a lot of work to get to the Fischer projections, but once you're at there, you can say, oh, I can immediately start to interrelate all my structures. And we know that there are 8 D sugars. There are 8 D sugars because the D indicates the position at 5 is always fixed, and we can permute the positions 2, 3, and 4 to come up with the other stereoisomers. I'm not going to bother to ask you to know them, but they are allose, altrose. They have cool names. Glucose, mannose, gulose, idose, galactose, and talose. So these are the 8 diastereomeric D sugars. All right, well, I think that wraps up what I want to say about the introduction to the structure and stereochemistry and sugars. We will pick up next time talking from the 4-carbon sugars on up and then move into reactions of sugars.